skills and concepts. It's a phrase that comes out of the literature in the mid-80s, mid to late 80s. In the typical math book, and hence in the typical math course, manipulative skills are developed first so that they can be used while trying to master concepts using as the paradigm pencil and paper as the working tool. But now with Maple available, they can provide those manipulations at the outset. You can emphasize concepts first, get the concept across, and you can use Maple to implement manipulations that then need to be examined. And when this big picture of how the concept and the manipulations fit together, then the students can turn their attention to mastering those skills that are essential to further learning. One of the first things that shows up in Integral Calculus course is an exploration of the Riemann sum as part of the definition of the definite integral. So here's a problem that lets us explore that. We have a function f of x. We want to look at the area under that curve bounded by that in the x-axis, and then set up a Riemann sum approach to finding that area. I'm going to start with a numeric graphic approach, and I'll use a tutor to do that, and I'll show you what these tools are. First, I want to load the Student Calculus 1 package. Now, Maple has many packages, over 100. It's just the way the library code is organized. It's all part of Maple. So I've brought now some new functionality into Maple's memory, and I want to define this function. So I select it, and I hold down the control key while I pull it over. That is what I call a control drag. It's equivalent to a copy paste. You can do that in Windows and also in other operating systems like Linux and a Mac. So to define that function, I go to the context panel and I select this option, assign function, and that takes care of all of the machinery to define the function whose name is f and whose rule is 6 plus x minus x squared. I want to draw its graph. Type f of x, hit the enter key, and make use now of this plotting tool called the plot builder. So the plot builder will let me draw this 2D graph, and you can see that the default minus 10 to 10 on the x-axis is way too big. I'm really interested in what looks like minus 2 to 3. So let's make that change. Negative 2 to 3. And it would appear that this is the area that we want to calculate. Now, if we want confirmation that the intercepts are minus 2 and 3, let's type f of x equals 0, hit the enter key. Basically, we're going to have Maple solve for the x-intercepts. There's a solve option, take the simplest solve, and we see that yes, negative 2 and 3 are the two intercepts. Okay, now I want to make use of the Riemann sum tutor. Now, tutors are pop-up tools. They're housed here under tools, tutors, and each different subject area has a bunch of such tutors. And we want the Riemann sums tutor. Now, if I launch it from here, I've got to put the function into it. If I type f of x, if I can get my fingers to work, and I will do from the context panel, evaluate and display in line, and there's a keyboard equivalent. In fact, there are two keyboard equivalents. I use Control equal, but Alt Enter is equivalent. So now I can go down here to Student Calculus 1, Tutors, and I now have access to any tutor that makes sense to inflict on this expression, and I want Riemann Sums. So the Riemann Sum tutor pops up, and you'll notice that the function is in there. It does not have the x-intercept, so -2 to 3. If I click display, I have a graph of the function between -2 and 3, and a default 10 rectangles whose heights are determined at the midpoint of each subinterval. Down here you see the actual area under the curve and the approximate area computed with these 10 rectangles. We can easily change the kind of Riemann sum. Left Riemann sum, you have a recomputation of the approximate area. You can do left, right, midpoint, upper, lower, and even random, where you pick a random point in each subinterval. You'll notice down here there is a command Riemann sum that's implementing these computations. If you wanted to work with the command, you could copy and paste it. I think having this tutor where you just need to press some buttons, click some boxes, is an easier way of getting at this functionality. Okay, so we experiment with the number of rectangles. We can animate, and you see more and more rectangles until the area is completely filled. That's the idea behind area by a Riemann sum. So after these manipulations are done, some sense of what a Riemann sum is comes across. Now, having explored graphically and numerically, let's see if we can explore analytically. And we'll make use of this task template. Now, what's a task template? Go over here to Tools, Tasks, and Browse, and you get the table of contents of the task templates. This is Integral Calculus, Integration, Riemann Sums. Let's do left sum. This is the task template. You can insert it by clicking one of these insert buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. And I've got it already embedded in my workspace. So the first thing you want to do is you want to have this template know the function. So I'm going to use the tab key. It selects the field. I type f of x, hit the enter key. I need to put in the domain, and that's -2, 3, hit the enter key. Now we've explored with a finite number of rectangles, so I'm going to put a placeholder in. And then I'm going to hit the enter key, and this command is going to execute. That Riemann sum command is going to execute, and it's going to get its input data from these equation labels. Pulls in the data that it needs from those equation labels. You hit the enter key, and this is the Riemann sum, left sum, for this function. At this point in the course, there's a break in which the student has to master the algebra of converting this expression to something that you can take the limit of. By the time that algebra is mastered, the student has lost track of why they're doing this. What you want the student to see is that area under the curve is the limit of the Riemann sum. So right here, let Maple provide the simplification of this expression. And continue with the idea, limit of the Riemann sum. Limit of the Riemann sum. Okay, so we want to take the limit. Now, we could find a limit operator here in the context panel, or we can go to the calculus palette. It is a limit operator right there. Now, I've got a limit operator in my favorites palette. Favorites palette generally starts out empty when you first install Maple. If you find something you want to make use of repeatedly, right click on it and you have this option, add to favorites. Okay, so let's put in this limit operator. We are letting n, and you use a tab key. We're going to go to infinity. So there's an infinity symbol, which you probably get from here someplace, common symbols, and you just use that right click trick, tab over, and I want to take the limit of this expression. Well, the simplest way to access that is to use its equation label. So for that, Control L, L for the insert label tool, put 5, hit the enter key, and I want to know what that limit is. So I'm going to do this evaluate and display in line, so I do a Control equal, and there is an exact value for that limit. And if I want to approximate that to a certain number of places, we get the number that we saw in the test in the tutor. And finally, let's implement the solution from first principles. Now, the function has already been defined, so we don't have to do that. Step size, b minus a over n. So that's 3 minus a negative 2, that's 5 over n. So let's do 5/n, and I want to assign that a name. So assign to a name here in context panel, and I'll call that step size h. We have to take the limit of a Riemann sum. So here's the limit operator. We're going to let n go to infinity. And what are we taking the limit of? Well, it's a sum. Now, there is a sum operator here in my favorites palette. It comes out of the expression palette. There it is, right? And I have it in my favorites palette. So there's this operator. I like k to be my index. This is a left sum, so I'm going to start from 0 and go to n minus 1. And what am I taking the limit of the sum of? Areas of rectangles. The rectangle height is the function evaluated at the left edge of each subinterval. So those left edges start at negative 2. And then you advance to the right k steps of size h. Now, if you're watching carefully, you'll notice that I put a space between the k and the h. That's implied multiplication. That's my preference. That's what I see in my math books. I don't see an operator between k and h for multiplication. So another space for multiplication, and then h. And what is this worth? Well, do a control equal, and we see that 125 over 6. When the student has mastered this notion of limit the Riemann sum, then if it's important, go back and play with these summations to show how this becomes that. But that's a side show to the notion or concept of limit of the Riemann sum. After introducing the definite integral as a way of finding area under a curve. One extension of that is to find the area bounded by two curves. Here's a problem like that. It's got a little bit of a wrinkle to it. One curve is a parabola opening upwards. The second curve is a parabola opening downwards, but we don't know the value of A for that second curve. It's determined by the condition that between these two curves there has to be an area, and here I've just picked the number 100. Well, let's see how we might solve this problem. We need to intersect the two curves to find the bounds on the x-axis for the range across which we're going to integrate. So we need to set y1 equal to y2. Equivalently, we could set the difference, y2 minus y1 equal to 0. And that's actually what I'm going to do. I'm going to grab this y2, and then I'm going to subtract an x squared. That's y1, and I'm going to hit the enter key. Now, to solve this, we need to set it equal to 0, but Maple's solve command assumes that you meant to set it equal to 0. So I want to solve this for x. And there are two solutions. If you look carefully, it's plus or minus a over the square root of 2. So now we're ready to integrate. And I will make use of this definite integral template. Comes from the calculus palette. I've shown how to put things into the favorites palette. So here's the definite integral we have to evaluate. That's the template. So now we're going to set the lower limit, negative a slash, and here is a square root template, 2. And I've got that from the expression palette. Put it in my favorites. Tab up here and put a slash, again, square root 2. I tab over to the integrand. Now notice that the integrand is actually right here. It has an equation labeled 1, and I can use that to represent the quantity a squared minus 2x squared. And since there really should be parentheses around that, I'm going to put a pair of parentheses, then do control L1, tab over here to the x, set that equal to 100. Now, if you would prefer seeing what you are actually integrating, right-click on that equation label and change label to label reference, and you see the a squared minus 2x squared. Hit the enter key. The integral is evaluated, and we see we have a cubic in a to solve. Well, we can go to solve, pick numerically solve, and we have this numeric value. Let's do a control L3, and let's solve this time analytically. So solve, and you get 3 solutions now. These 2 solutions are complex because that I is the square root of minus 1. This is the one real solution. Let's take a look at that. The one select element 1. Okay, so this is the one real solution. And if we float that by let's approximate 10, we see that they are essentially the same numbers. The next thing that typically comes up in one of these courses would be methods of integration. And the big 3, integration by parts, trig substitution, and partial fractions. Well, I'm going to take a problem in partial fractions. Let's make this a bit bigger. Okay, I have a rational function, and there were two things to do. One is the actual algebra of the partial fraction decomposition, and then there are the issues of integrating those fractions, and some of the techniques that the student has had to master up until this point come into play. Let's look at the algebra of the partial fraction decomposition. And there's a variety of ways of tackling it. First, we're just going to have Maple tell us what the decomposition is. So let's drag this down and assign function. Type f of x, and let's do a control equal. That echoes the rule for the function. Conversions here in the context panel. Partial fractions, x is the variable of decomposition. There is the partial fraction decomposition. So if what you need is the partial fraction decomposition, get it instantly. Another way to look at partial fraction decomposition is as an identity. So the template fractions need to be written first. I'll write 1 over. Here's the first denominator. You can see from the factored form here. X squared plus 4. The numerator has to be a linear thing. A space x4 implied multiply plus b. The second fraction has as its denominator x squared plus 1. And its numerator is also a linear, so cx plus d. I want to give this a name, so I will assign to a name. I will call it g. The identity that we're setting up is f of x equals g. We want to find the 4 coefficients, a, b, c, d, that makes this an identity in x. So if you go here to solve, you will see solve as identity. The independent variable is x. It's an identity in x, and the coefficients to be found are a, b, c, d. And Maple computes these 4 coefficients, and if you want to put them back into g, we could use this substitute into and substitute that into g, and we get back the partial fraction decomposition. There's a stepwise partial fraction task template. We've seen the table of contents for the task templates. This is the task template. It takes the student through one procedure for getting the partial fraction decomposition. There are many different ways to approach this. So it says here, begin by entering f of x. If the denominator is not factored, this button will do it, but the denominator is already factored. Now, the decomposition requires the template. We have already stored that as g, and this box will check to see if that g is correct. There's no sense going further if the template is not correct. Now, there are different ways to approach the algebra here. I like to multiply through by this denominator and clear all denominators. That leaves this numerator equal to this expression on the right, because you multiply each member, the two fractions in G, you multiply by that common denominator. And then you collect like terms, all the x cubed terms, all the x squared terms, you bring these over, you get 0 on the left, and you have this polynomial on the right, which must be identically 0. So each coefficient needs to be 0. That's where you get your equations. Take this one here. This is the constant term, b plus 4d minus 1, that equals 0, etc. Then you solve those equations, and you put those numbers back into your partial fraction decomposition template. That is how you are led through stepwise a procedure, a path through the algebra of getting the partial fraction decomposition. Well, of course, we would like the student to be able to implement these steps from first principles without the aid of that test template. So let's try this. F of x equals g. Now remember what we did. We multiplied through by this common denominator. But Maple wants us to work on an expression rather than any equation. So let's move everything to the left and take off that equals 0. So we'll grab the left-hand side. So now we have just an expression to work with. Multiplying through by that common denominator, and we really only need to worry about the numerator at that point. So if we simply select the numerator of this expression, it will be equivalent to multiplying through by the common denominator. We should collect with respect to x, and then pick off the coefficients of x. When we have these expressions, each of which must be set equal to 0, Maple solve command will interpret our intention as meaning that we want that to be equal to 0. And we can use a substituting into the template G to obtain the partial fraction decomposition. Having obtained this partial fraction decomposition, we see there are two rational functions to integrate. So let's get the indefinite integral of those two fractions. To begin, why don't we just get the antiderivative? Let's see what Maple's got to say about the antiderivative. So we go up here to the calculus palette, and there is an indefinite integral template in there. Type f of x, tab over here, and do a control equal, and we see that there are two terms. One is an arctangent, and one is a logarithm. If you look really carefully, you can see this is the one that probably turns out to be the logarithm, dx over du over u, and this is roughly the arctangent. Let's make use of the integration methods tutor to do a stepwise interactive integration. So to access the tutor, I'm going to load the Student Calculus 1 package. So Tools, Load Package, Student Calculus 1, f of x, control equal. So now we see the rule. And if we go here to Student Calculus 1, Tutors, we pick Integration Methods. So that's the Integration Methods tutor. I think I'll move this over to here. Now, The order in which Maple will split this when we apply this partial fractions rule button can change from one session to another. You can see here that we have 1 over x squared plus 4 is the first fraction. So when we now split that with the sum command, the next operations that we perform will be performed on this leftmost of the two indefinite intervals. The instructions here have to be interpreted as which instruction applies to which. X squared plus 1 appears in this fraction, so that's going to come second. So first we want to make this change of variables. Maple would suggest, if we would query it, to make the transformation x equals 2 tan z for this. So change, and we write here x equals 2 times tan of z. And we apply that change. And that brings us to this form, 1/2 dz, the integral of a constant. So it's 1/2 z. And then we select, where is it? Revert. And we get 1/2 arctan x over 2. That's this term. Now to do the second of these two indefinite integrals, we'll make this change of variables. U equals x squared plus 1. U equals x squared plus 1. And we get 1 over 2u. Now either we deal with this constant multiple and take the 1/2 out first, then we can try the power rule. We get that logarithm, and then it's another revert. Let's stretch this down a bit. And we have the log term, log x squared plus 1 over 2. Now, when we click close, we will have written down in our workspace the steps that we went through, annotated. So there's a record of what was done in that tutor. Now, this annotated solution can be obtained in Maple directly by simply asking for it. We've already installed the Student Calculus 1 package. We don't have to do that again, but we want to write the indefinite integral, so we'll make use of the same template we made use of before. F of x, tab x, go here to Student Calculus 1. In the context panel, and select all solution steps, at which point we get an annotated stepwise solution produced directly. Another item in the Calc 2 course that people ask about is, what does Maple have to offer for visualization of surfaces and solids of a revolution? So let's take this problem down here. I have a region formed by these bounding curves. Y equals x squared. So here's y equals x squared. X equals 1. x-axis, and that's rotated around the line x equals 2. Now, of course, that's enough to be able to visualize the region and the solid being produced. Of course, and this is why people ask, what can Maple do to make this visualization easier? Well, we're going to find the volume of this solid revolution, and we'll try it with both disks and shells. So before doing any calculations, let's see what we can do about visualizing this region, this solid. The plane region is kind of this reddish color. It's rotated around the line x equals 2. There is an outer radius is larger than the inner radius. This is an animation of the rotation of that region. Oh, I guess I could set this to continuous rotation. It would just keep going round and round. Okay. Now it would be nice to see that region traced out, sort of a smoke trail kind of thing. So this one, I will set it continuously and have it oscillate back and forth. And now you can see the region rotating and creating this solid of revolution. So that's what we want to compute the volume of. And that's the kind of visualization that people look for when they say, can Maple draw this and can Maple draw that? I think I best stop these So let's roll up our sleeves and tackle this by disks. We want to visualize the disks. We have some pictures here. If we rotate y equals x squared, we get this outer boundary. This would be the solid. If we rotate the inner radius, x equals 1, we get this plug. And that's removed from this solid, leaving this solid. Slice it into a stack of disks. So actually, they're rings or washers. And here is one washer. Inner radius, little r, outer radius, big R. And that's why we draw outer radius, inner radius, so that we can give analytic expressions for these radii. Well, now we're ready to implement a solution from first principles. The idea for this formula comes from pi r squared times the height. Each disk has an outer radius and an inner radius that give you area, pi r squared. Then you thicken it, dy, because these are horizontal slices. And this then becomes the integral that we have to evaluate. What is big R? Well, from here you can see big R is 2 less this piece out here, but that's an x-coordinate. But x-coordinate has to be expressed as a function of y, so it's x of y. Little radius is 1. So we can begin building up this integral. We need a pi. Okay, so here's a pi in my favorites palette. I get it from common symbols. I find it here. I right-click on it, add to favorites. That's how I populate my favorites palette. There's a pi. Now, you can also get a pi from the keyboard by pressing 3 keys simultaneously, down, up, the next key you hit will come out in Greek. And those three keys are Control, Shift, G. G is for Greek. Hit the letter P, and you get a pi. There is a full Greek palette. Here, full Greek palette. And there's a pi in it. I find hunting through that palette more tedious than doing it from the keyboard. Okay, space for implied multiplication. I have a definite integral template, which I got out of the calculus palette. It's in my favorites palette. I'm integrating 0 to 1. I need parentheses to make this look mathematically correct. I have something square, big R squared, that's something squared. And then I'm going to subtract 1 squared, which is 1. And inside here for big R, it's 2 minus the square root of y. That square root template can be found in the expression palette. And then I tab over here, and that's y. Control equal will give me 5 pi upon 6. Volume computed by disks for something rotated around a vertical axis. To get the volume by the method of shells, we can make use of this volume of revolution tutor. Now, I'm going to obtain the tutor from this tools menu. Tutors, calculus of a single variable, volume of revolution. So here is the tutor. Now, we have to make some insertions of data. The f is x squared. The g is 0. That's the bottom. The rightmost boundary is set by setting the endpoints 0 to 1. Now, the default says we're going to rotate around a horizontal axis, in which case you have access to the disk method. But we are integrating or rotating around a vertical axis, and instead of seeing or having access to disks, you now have access to shells. But the axis of rotation is displaced 2 units from the coordinate axis. And if you display now, you'll see something that begins to resemble the figure that we had seen earlier. If we go to plot options and pick constraint scaling and change the frame to frame rather than normal, you will, it's less cluttered, and you will see the solid. You will see the region right here that's being rotated. Here's the axis of rotation. Here you see the integral that gives you the volume, 5 pi upon 6. This is the integral that you would use to do shells. And this is the approximate value. So select shells, click display, and you see a stack of shells. You also see an approximating Riemann sum. It's formed by the midpoint method, and you have left, right, or midpoint, and it has 6 shells. If you click animate, you will see one shell traversing the solid. So this helps give a sense of just what it is that we are computing. you can see here the volume of revolution command. I think it's easier to get some of this information from syntax free from the tutor rather than to begin by trying to figure out the syntax of this volume of revolution command. So I think put that away. And let's see what's involved in obtaining a solution by shells working from first principles. Well, you can see from this formula here, 2 pi r. Now, 2 pi r is the circumference of the vertical shell. L is its height. The radius is 2 minus x. And we can see that from this picture. It's 2 minus 2 minus x. And the height of that shell is given by y equals x squared. So these are the ingredients of this integral. You saw how to implement an integral. Not going to reproduce that. Leave that for the participant. But you can see it's the same thing. You need 2 pi definite integral and these expressions. Now, in addition to volumes of a solid of revolution, calculus books also contain a volume by slicing. Some books put slicing first. Some books put a revolution first. So here's a problem where we'll calculate a volume by slicing. And the hard part here is to visualize the region. Here's the description verbally. Base in the xy plane is a region bounded by the x-axis. The curves y equals sine x and x equals pi over 2, and whose cross-section parallel to the yz plane would be an equilateral triangle. Well, we clearly need some help here in visualization. This is what the solid looks like. This is an animation that shows, I think I'll have this thing back and forth. That shows the cross-section, which is an equilateral triangle, traversing the solid. This curve in the back is y equals sine x from 0 to pi over 2. This is an equilateral triangle. And I think I'll stop that. To set up the appropriate integral, I think we need one more picture. Okay, this is a picture of the cross-section, equilateral triangle. Now, this distance is sine x. And that's why I have the base of that triangle, a equals sine x. This is 1/2 sine x over this side. This is 1/2 on that side. It's an equilateral triangle, so this edge is sine x also. Now, this is a solution for the area of this triangle using similar triangles. I think it's a little bit easier if you use the formula area is 1/2 AB sine C. Sine C is a 60-degree angle. So the area of this triangle is 1/2 sine times sine. You get sine squared. Sine of 60 degrees square root of 3 over 2. And so the integral that you need to set up is root 3 over 4 sine squared 0 to pi over 2. So root 3 over 4. We need an integral 0 to pi over 2, and it's sine squared x. And you have an answer, root 3 over 16 pi. There's another big chunk of work in the Calc 2 curriculum, applications of the integral. The idea, I guess, is to illustrate that an integral is a summation process. And so work and fluid pressure are two of the applications. Here's one in fluid pressure. It's the total force on a dam. It happens to be a trapezoidal dam. I don't know how many dams are in that shape, but a trapezoidal dam, and you have the dimensions and how much water is behind it. What's the total force? The idea behind it is to see integration as a summative process. Unfortunately, I think many students lose that point because they don't have the problem-solving background that it takes. A solution for this problem begins with two physical facts. Pressure at depth D is fluid density, 62.5 per cubic foot, times the depth, and the force on an object at that depth is pressure times area. So here's a pressure, and then there's force. Picture. Here's the trapezoidal dam. 15 here, 25 across here, so this little piece is 5. This is a strip of area, it represents a strip of from the slab of water in behind. Origin at the bottom, measure y upwards as positive. There's a depth of water is 10, so this distance down, this is the D, the depth that you use up here in computing the pressure, is 10 minus y. We need this changing length. Well, this chunk of it is 15, so what's this little piece over here? We do that by similar triangles. But before we can apply similar triangles, we need the length AE. In this right triangle, ADE, you can use the right triangle rule, 15 squared minus 5 squared, because this edge is 15, this little piece is 5, so it's 10 root 2. Then you set up similar triangles to get this little piece BG. BG is to y as 5 is to AE, but AE is 10 root 2, so BG is y over 2 root 2, the 5 cancel to the 10. This length, BH, is 15 plus 2 of these little pieces, so it's 15 plus 2 of the things we just computed, y over 2 root 2, so the 2's cancel. So that's this length, thicken it by dy, and that's the area of this strip, infinitesimal area. Okay? The pressure at depth D is 62.5 times this depth, 10 minus y, and so the force on this horizontal strip is 62.5, 10 minus y, that's from here, and 15 plus y over root 2 dy from here. Sum that pressure, or that force on that strip across all of the water, so that's an integral 0 to 10 of PdA, 62.5 d dA. All of this stuff appears as the integrand. To evaluate that integrand, let's just drag it down here and do a control equal. That's the total force on that dam.